Something just appeared on the sun that wasn't there 2 days ago. Sunspot AR-4366 materialized in 36 hours flat, transforming from absolutely nothing into a magnetic monster capable of unleashing the kind of solar storms that make power grids collapse and satellites go silent. This isn't supposed to happen this fast. Not during solar cycle 25, which was predicted to be manageable, predictable, almost boring. But here we are at the cycle's peak, watching cosmic ray levels plummet 20% while a hyperdense, multi-core sunspot rotates directly toward Earth like a loaded cannon finding its target. Scientists are asking two questions they can't yet answer. Is this the volatile X-factor event we've been dreading? Or is AR-4366 just the first visible symptom of something far larger shifting in our solar environment? Stay until the end, because what's really happening goes deeper than one sunspot. The sun is sending signals we're only beginning to understand, and the timeline is already counting down. Subscribe and follow along, because as the sun rotates AR-4366 into firing position, what we discover over the next 72 hours will determine whether we truly understand our star's behavior or have been fundamentally wrong about the forces driving solar cycle 25, a cycle that's been defying predictions since it began and might be revealing something essential about stellar magnetic reversals that we've overlooked for decades. 36 hours. That's all it took for something invisible to become hypermagnetic and potentially catastrophic. On the surface of our sun, a sunspot group designated AR-4366 materialized faster than the physics textbooks said it should, and now it's rotating directly into firing position at Earth. We're not talking about a gradual buildup over weeks or months like most solar active regions. We're talking about an explosive birth that has solar physicists checking their instruments twice because the timeline doesn't make sense. AR-4366 isn't just large. Size, frankly, is overrated when it comes to solar threats. What matters is density, and this particular monster is dense in all the wrong ways. It's a multi-core sunspot group, which means instead of one concentrated magnetic structure, you've got several distinct cores packed together, like coiled springs sharing the same box. Each core generates its own magnetic field, and when you cram multiple opposing magnetic polarities into close proximity, you create what solar physicists politely call unstable configurations, and what the rest of us might call a loaded weapon. The magnetic field strength in AR-4366 measures between 2,000 and 4,000 Gauss. To put that in perspective, Earth's magnetic field at the surface is about half a Gauss. You're looking at a magnetic environment 4,000 to 8,000 times stronger than what protects us from cosmic radiation. That kind of density doesn't just happen. It requires specific conditions in the sun's interior convective zone, a churning chaos of superheated plasma that occasionally decides to concentrate all its magnetic fury into one location. When it does, the result is what we're seeing now. Here's where it gets interesting. Most active regions on the sun take days, sometimes weeks, to organize themselves into coherent sunspot groups. The magnetic flux tubes have to rise through hundreds of thousands of kilometers of dense plasma, break through the photosphere, and arrange themselves into stable or semi-stable configurations. It's a process. AR-4366 skipped the process. In less than 2 days, it went from nothing detectable to a fully formed, magnetically complex threat. That's not supposed to happen during solar cycle 25, which has been notably more organized and predictable than previous cycles. Until now. The positioning is what keeps me up at night. Between February 2nd and February 5th, 2026, AR-4366 will be facing Earth. Not partially, not at an angle. Directly facing us during what solar forecasters call the blast zone window. When a solar active region is positioned at the center of the sun's visible disk from Earth's perspective, any eruption it produces has the highest probability of impacting our magnetosphere. It's simple geometry, but geometry has consequences when you're dealing with billion-ton clouds of magnetized plasma traveling at millions of kilometers per hour. January 2026 already gave us a preview of what this solar cycle can do when it gets angry. We experienced severe geomagnetic storms, the kind that push aurora down to latitudes where people aren't used to seeing them. We also had proton storms intense enough to trigger radiation warnings for polar flight routes. Those events happened when the sun was supposedly between major active regions. Now we have AR-4366, and it's showing up at exactly the wrong time, or exactly the right time, depending on whether you're a solar physicist excited by data, or someone who relies on GPS and power grids. The X-ray flux data is what really bothers the forecasters. Between solar events, the sun's X-ray emissions should drop to a relatively flat baseline. It's what we call a quiet sun state. AR-4366 hasn't allowed the sun to go quiet. The baseline is jittery, elevated, showing signs of continuous low-level activity, even when there's no major flare occurring. That pattern suggests loading, not release. It's the difference between a volcano that erupts and then goes dormant versus one that keeps rumbling and venting gas between eruptions. The rumbling volcano is telling you something about what's building underneath. So here's the central question, the one that should make you pay attention. Is AR-4366 a release valve for built-up magnetic stress in the sun's interior? Or is it a pressure signal, a symptom of something larger organizing itself beneath the surface? Because if it's the latter, this 36-hour explosion isn't an isolated event. It's the visible manifestation of deeper processes we're only beginning to understand. And those processes don't care about our satellites, our power grids, or our assumptions about how solar cycles are supposed to behave. This sunspot exists in context, and the context is troubling. Solar cycle 25 was supposed to be moderate, manageable, predictable. Instead, we're seeing rapid formation events, extended periods of elevated activity, and a cosmic ray environment that suggests the sun's influence is stronger and more extensive than the standard models predicted. AR-4366 might flare tomorrow, or it might remain relatively quiet as it transits across the solar disk. But either way, it's a symptom of something deeper, something structural happening to our star. And that's the story nobody's talking about yet. Position matters more than power when you're talking about solar eruptions aimed at Earth. You can have the largest X-class flare in recorded history, but if it erupts from the sun's eastern or western limb, from our perspective, the worst of the blast will miss us entirely. It'll head off into space, maybe hit Mars or Venus or nothing at all. AR-4366 won't have that luxury, and neither will we. It's rotating into central disk positioning, the solar geometry sweet spot, where an eruption doesn't have to guess where Earth will be. It just has to fire. Central disk positioning means any coronal mass ejection from this region has Earth directly in the crosshairs. The math is straightforward. A CME erupting from within 30 degrees of the sun's central meridian, as viewed from Earth, has approximately an 80 to 90% chance of impacting our magnetosphere if the eruption is powerful enough and directed outward. AR-4366 will be well within that window for at least 3 days. 3 days of elevated probability, 3 days where a single magnetic reconnection event could send billions of tons of magnetized plasma directly toward us at speeds up to 3,000 kilometers per second. But here's what most coverage gets wrong. Earth-facing doesn't automatically mean disaster. The sun produces dozens of CMEs every day during solar maximum, and most of them are weak, diffuse, or poorly organized. They hit Earth's magnetosphere and barely register on geomagnetic indices. What matters is the combination of factors, the convergence of position, magnetic density, and internal configuration. AR-4366 has all three, and that's why solar forecasters are watching it with the kind of attention usually reserved for much larger active regions. Magnetic contention is the key concept here. When you have a single core sunspot, even a large one, the magnetic field lines are relatively organized. They emerge from the photosphere, arc through the corona, and return to the surface in a predictable pattern. Stable, or at least stable enough. But when you have multiple cores packed together, each with its own magnetic polarity, you create zones of contention where opposing field lines twist around each other. Imagine electrical wires knotted together, each carrying current in opposite directions. Eventually, something has to give. In solar physics, what gives is called magnetic reconnection, and when it happens in a dense, multi-core active region like AR 4366, the energy release can be spectacular and violent. The X-ray baseline pattern I mentioned earlier is the evidence that this contention is ongoing. Instead of seeing discrete flares separated by quiet periods, we're seeing a continuously elevated state. The sun is staging higher energy levels between events, like an athlete who never fully recovers between sprints. That's unusual even for solar maximum, when activity is expected to be high. It suggests the magnetic structures within AR 4366 are under continuous stress, continuously reorganizing, and continuously on the edge of major reconnection events. Forecasters are putting the probability of M-class or X-class flares from this region at around 80% over the next 72 hours. Let's talk about what that number actually means. An M-class flare is medium intensity, capable of causing brief radio blackouts on the sunlit side of Earth and minor radiation storms. An X-class flare is the big leagues, the kind that can cause widespread radio blackouts, trigger radiation warnings for aircraft and spacecraft, and, if accompanied by a fast CME, produce severe geomagnetic storms. 80% probability means that if you ran this scenario 100 times with similar magnetic configurations, you'd expect a significant flare in 80 of those runs. Those are not comforting odds if you're managing satellite operations or electrical grid infrastructure. But probability is only half the equation. The other half is impact severity. And that's where the geometry becomes critical again. A geo-effective event is one that doesn't just happen, but happens in a way that matters for Earth's technological systems. It requires not just a powerful flare, but a well-aimed CME with the right magnetic orientation. When a CME hits Earth's magnetosphere, the interaction depends on the magnetic field embedded in the plasma cloud. If that field is oriented southward relative to Earth's magnetic field, you get strong coupling, strong energy transfer, and potentially severe geomagnetic disturbances. If it's oriented northward, the interaction is much weaker. We won't know the magnetic orientation of any CME from AR 4366 until it's already on its way, traveling through space at speeds that give us between 12 and 72 hours of warning, depending on the eruption velocity. What could a geo-effective event actually do? The worst-case scenarios involve power grid failures in high-latitude regions where geomagnetically induced currents can overload transformers. We've seen this before. The Quebec blackout of 1989 was caused by a severe geomagnetic storm that induced currents strong enough to trip circuit breakers and collapse the entire provincial grid. 6 million people without power for 9 hours. And that was from a storm that, by modern standards, wasn't even the worst we've recorded. The Halloween storms of 2003 were stronger. The Carrington event of 1859 was orders of magnitude stronger, and if something like that happened today, the economic damage would be measured in trillions of dollars. Satellite operations are equally vulnerable. High-energy protons from solar flares can degrade solar panels, damage electronics, and cause bit flips in computer memory. Communication satellites in geostationary orbit are particularly exposed. GPS satellites, which our entire navigation infrastructure depends on, can experience timing errors and signal degradation during severe space weather events. Aviation routes over the poles have to be rerouted because the radiation exposure becomes too high for flight crews. These aren't theoretical concerns. They're operational realities that happen multiple times per solar cycle. So when we say there's an 80% chance of significant flaring from AR 4366 during its Earth-facing transit, we're not fear-mongering. We're describing a probabilistic convergence of geometry and physics that has real-world consequences. The question isn't whether AR 4366 will produce a major flare. The odds suggest it will. The question is whether that flare will be accompanied by a fast, well-organized, southward-oriented CME that hits Earth at the worst possible time. And we may be closer to that scenario than the models would have predicted just a month ago, based on how this solar cycle was supposed to behave. Here's the uncomfortable reality. Solar forecasting is getting better, but it's still fundamentally limited by the fact that we can't see beneath the sun's surface. We can't watch magnetic flux tubes rising through the convective zone. We can't predict with certainty when or where they'll emerge. We can only observe what's already visible and extrapolate from historical patterns. AR 4366 didn't follow the patterns. It appeared too fast, organized too quickly, and now it's in exactly the wrong position at exactly the wrong time in the solar cycle. Is the geometry alone enough to push us into a new solar danger zone? Maybe. Or maybe the geometry is just making visible what's been building all along. The sun isn't calm between storms. That's the first thing you need to understand about our star's behavior during solar maximum. While we're down here on Earth experiencing what we call quiet periods between major space weather events, the sun's interior is anything but quiet. It's churning, convecting, generating new magnetic fields through a process called the dynamo effect. Imagine a planetary scale engine where superheated plasma rises, cools, sinks, and rises again in continuous circulation patterns. Now add rotation to that mix, the sun spinning at different rates depending on latitude, and you get shearing forces that twist and amplify magnetic fields. This is how the sun creates the magnetic flux that eventually erupts through the surface as sunspots and active regions. AR 4366's magnetic field strength of 2000 to 4000 Gauss isn't just a number on a magnetogram. It represents an enormous amount of stored energy, compressed into a relatively small area on the solar surface. To put this in human terms, imagine the magnetic field around a standard refrigerator magnet. Now multiply that by several hundred thousand. That's still not enough. The magnetic forces in a sunspot like AR 4366 are powerful enough to physically suppress the convection of hot plasma from the sun's interior, which is why sunspots appear darker than the surrounding photosphere. They're cooler because the magnetic field is so strong it interferes with the normal heat transport mechanism. When you pack opposing magnetic polarities together in close proximity, as happens in a multi-core sunspot group, you create magnetic tension. The field lines want to realign to find a lower energy configuration, but they're anchored in dense plasma that resists easy motion. Think of it as a compressed spring, but instead of mechanical potential energy, you're storing magnetic potential energy. The more compressed, the more twisted, the more opposed the polarities, the more energy is available for release. And when that release happens through magnetic reconnection, the energy doesn't just dissipate gradually. It converts explosively into kinetic energy of plasma and electromagnetic radiation. Solar physicists use what's called the spring-loaded model to describe this process. In the gradual stress release model, magnetic energy builds up slowly and releases incrementally through small flares and minor reorganizations. In the spring-loaded model, the energy builds to a critical threshold and then releases catastrophically all at once. Based on the X-ray flux behavior and the rapid formation timeline of AR 4366, we're looking at something closer to the spring-loaded scenario. The magnetic structures haven't had time to settle into stable configurations. They're still loading, still building stress, and the continuous elevated baseline activity suggests that partial reconnection events are happening constantly, rearranging the field lines without fully releasing the stored energy. Extreme ultraviolet wavelengths give us the best view of these dynamic plasma structures. Observations at 131 angstroms show us the hottest plasma in the corona, material heated to over 10 million degrees by magnetic reconnection and current sheets. At 171 angstroms, we see cooler material, around 600,000 degrees, which traces out the magnetic field lines as plasma flows along them. These wavelengths reveal something crucial about AR 4366. It doesn't look finished. The magnetic loops aren't organized into clean, stable arcades. Instead, you see chaotic tangles, small-scale brightenings, and rapid changes in structure over timescales of minutes to hours. That's the signature of an active region, still organizing itself, still building towards some future state we can't yet predict. This is where AR 4366 diverges from typical solar maximum behavior. During the peak of the solar cycle, we expect to see large, complex active regions. Absolutely. But we also expect them to take time to develop, to pass through recognizable stages of growth, maturity, and decay. The classic model describes a 3 to 5 day emergence phase, a week or more of peak activity, and then a gradual decline over 1 to 2 weeks. AR 4366 compressed the emergence phase into 36 hours and jumped straight to peak complexity. That's not how the standard model says it should work, which raises the question of whether something about solar cycle 25 is challenging the standard model itself. One possibility is that the sun's interior magnetic field is stronger or more concentrated than we expected for this cycle. Early predictions for solar cycle 25 suggested it would be relatively weak, similar to cycle 24, which was the weakest solar maximum in a century. Those predictions were based on observations of the polar field strength during the previous minimum and models of how that field gets transported and amplified through the solar interior. But predictions and reality don't always align, and we're now seeing evidence that cycle 25 is significantly more active than the early forecasts suggested. AR 4366 might be one manifestation of that discrepancy, a sign that the interior magnetic field reached critical threshold conditions faster and more powerfully than anticipated. The phase of the cycle also matters. We're not at the predicted maximum yet, but we're close, probably within a few months. This is traditionally when the sun produces isolated but powerful active regions, the kind that dominate the solar disk and can persist for multiple rotations. But it's also a transitional phase when the sun's global magnetic field is in the process of reversing. The north and south magnetic poles are weakening, fragmenting, and will eventually flip to opposite polarities. During this transition, the magnetic topology becomes more complex, more chaotic, and potentially more prone to producing rapid emergence events like AR 4366. What solar physicists suspect, based on the continued loading signatures in the X-ray data, is that AR 4366 hasn't finished evolving. It may continue to develop, to add magnetic flux, to increase in complexity even as it transits across the solar disk. Or it may remain at its current state, a loaded spring waiting for the right trigger to release its energy. Either scenario presents challenges for forecasting. We can estimate the probability of flaring based on historical data from similar active regions, but AR 4366's rapid formation means we don't have a complete historical analog. We're in uncharted territory, forecasting based on incomplete patterns. And here's the uncomfortable part. The storm might not just happen randomly. It might be structurally prepared by the sun, by processes in the interior that we can observe only indirectly through heliosismology and magnetic field measurements at the surface. The sun is telling us something through AR 4366, broadcasting a signal about its internal state. Whether we're interpreting that signal correctly, Whether we understand what it means for the coming days and weeks, that remains to be seen. But one thing is clear. The magnetic overload is real, measurable, and ongoing. The question is when, not if, it will find a release mechanism. And there's another cosmic signal most people are completely overlooking. A signal that suggests this isn't just about one sunspot or one active region. It's about the entire heliosphere shifting into a different operational mode. Sometimes what's missing tells you more than what's present. In mid-January 2026, cosmic ray detectors around the world and in space recorded something that should make anyone paying attention to solar activity take notice. A sudden, sharp decrease in cosmic ray flux of approximately 20%. This is called a Forbush decrease, named after physicist Scott Forbush, who first documented the phenomenon in the 1930s. And while Forbush decreases are common during solar maximum, the magnitude and duration of this particular event suggests something system-wide is happening to the sun's magnetic influence. Cosmic rays are high-energy particles, mostly protons, that originate from outside our solar system. They're produced by supernovae, active galactic nuclei, and other violent astrophysical processes in the galaxy and beyond. These particles travel through interstellar space at nearly the speed of light, and under normal conditions, a continuous flux of them rains down on the solar system. Earth's atmosphere protects us from most of this radiation, but cosmic rays still have measurable effects on everything from cloud formation to electronic systems in spacecraft and high-altitude aircraft. The sun acts as a partial shield against cosmic rays through its magnetic field, which extends far beyond the planets in a region called the heliosphere. This magnetic bubble is created by the solar wind, a continuous outflow of charged particles from the sun's corona that carries embedded magnetic fields. When the solar wind is strong and the embedded magnetic fields are intense, they deflect and scatter incoming cosmic rays, reducing the number that reach the inner solar system. When the sun is quiet and the solar wind is weak, more cosmic rays penetrate the heliosphere. It's a dynamic balance, constantly shifting based on solar activity. A Forbush decrease happens when a powerful solar eruption, typically a fast coronal mass ejection, creates a temporary magnetic barrier that sweeps cosmic rays out of its path. The decrease can be sudden, dropping cosmic ray levels by 10 to 30% in a matter of hours, and the recovery can take days or weeks as the disturbed magnetic field relaxes back to normal conditions. What's unusual about the January 2026 event is that the cosmic ray suppression didn't fully recover. Instead of bouncing back to pre-event levels, cosmic ray flux has remained depressed, hovering near what we call -10 levels, meaning 10% below the baseline we'd expect for this phase of the solar cycle. Extended cosmic ray suppression at solar maximum isn't unheard of, but it's also not typical. During previous solar maxima, we've seen Forbush decreases associated with individual events, followed by gradual recovery over weeks. What we're seeing now is more like a sustained suppression, as if the heliosphere has shifted into a more magnetically active state that's continuously excluding cosmic rays more effectively than the models predicted. This could mean the solar wind is stronger, more organized, or carrying higher magnetic field strengths than we expected. Or it could mean the global structure of the heliosphere is different, this cycle shaped by processes we don't fully understand yet. Think of the heliosphere as a magnetic bubble surrounding the solar system, inflated by the pressure of the solar wind pushing against the interstellar medium. The size and shape of this bubble change with solar activity. During solar minimum, when the sun is quiet, the bubble is smaller and weaker, allowing more cosmic rays to penetrate. During solar maximum, the bubble expands and strengthens, deflecting more cosmic rays. But the relationship isn't linear. A 10% increase in solar wind speed doesn't necessarily produce a 10% decrease in cosmic ray flux. The topology matters. The magnetic field orientation matters. And the interaction between the solar magnetic field and the galactic magnetic field matters in ways we're still mapping out. The provocative question is this: what if the sun's magnetic influence is stronger than we thought? Not just temporarily, not just because of one or two large CMS, but structurally as a baseline condition for this solar cycle. The cosmic ray data suggests that possibility. So does the rapid emergence of active regions like AR 4366, which require strong subsurface magnetic fields to form. So does the elevated geomagnetic activity we've been experiencing, even during supposedly quiet periods between major solar events. All of these observations point toward a sun that's magnetically more active, more influential, more capable of shaping space weather conditions than the early cycle predictions suggested. This doesn't mean immediate danger. Lower cosmic ray flux actually reduces radiation exposure for astronauts and high-altitude aviation, so in that sense it's beneficial. But it does change our baseline understanding of the space environment. If the heliosphere is more magnetically active, that has implications for long-term space exploration, for satellite design, for understanding how the solar magnetic field couples to Earth's magnetosphere. It also raises questions about what happens when the sun eventually returns to solar minimum. Will the cosmic ray flux rebound to previous levels, or will we see a persistently altered state? The counter-narrative here is important. This is not about mystical solar influence on human consciousness or alien mind control through suppressed cosmic rays. Those are fringe ideas with no scientific support. What we're discussing is measurable magnetism, documented changes in particle flux, and observed correlations between solar activity and space environment conditions. The science is solid, even if our understanding of the underlying mechanisms is still evolving. We have satellites measuring cosmic ray flux in real time. We have ground-based neutron monitors that have been operating for decades, providing continuous baseline data. The Forbush decrease in January 2026 is in the data, unambiguous and quantifiable. What this cosmic ray signal tells us is that AR 4366 exists in a larger context. The sunspot isn't an isolated phenomenon. It's part of a system-wide change in how the sun is expressing its magnetic activity during the solar cycle. The suppressed cosmic rays are one signal. The rapid active region emergence is another. The elevated X-ray baseline between events is a third. Taken together, they paint a picture of a sun operating at the high end of its expected range, or possibly beyond it. And that leads us to the broader question of what's actually driving this unusual cycle, which brings us to one of the most fundamental processes the sun undergoes: the magnetic reversal. Every 11 to 12 years, the sun does something simultaneously mundane and profound. It flips its magnetic poles. North becomes south, south becomes north, and the entire global magnetic structure of our star reverses polarity. This isn't a sudden event like throwing a switch. It's a gradual process that takes months, sometimes years, involving the transport of magnetic flux from the active latitudes toward the poles, the weakening and fragmentation of the old polar fields, and the emergence of new opposite polarity field at high latitudes. We're in the middle of that process right now during solar cycle 25, and the timing matters because magnetic reversals coincide with solar maximum and are associated with increased complexity in the sun's magnetic topology. Imagine taking a bar magnet and gradually demagnetizing it, then remagnetizing it with opposite polarity. That's the simplified version. The reality is far more chaotic because the sun isn't a solid bar magnet. It's a rotating ball of plasma with magnetic fields generated by internal dynamo processes that vary with depth and latitude. The polar field reversal happens because magnetic flux from decaying active regions at mid-latitudes gets transported poleward by meridional circulation, a slow flow pattern in the solar convective zone that acts like a conveyor belt. As this opposite polarity flux accumulates at the poles, it cancels out the old polar field and eventually reverses it. During the transition, when the old polar field has weakened, but the new field hasn't fully established itself, the Sun's global magnetic structure becomes more complex and more prone to producing strong outliers. This is exactly the phase we're in now. The polar fields are fragmenting, showing mixed polarities at high latitudes, and the corona shows signs of a more disorganized large-scale magnetic structure than during the rising or declining phases of the cycle. This transitional chaos is fertile ground for rapid active region emergence, like AR 4366, because the subsurface magnetic field can organize into strong concentrations without the stabilizing influence of a coherent global field. What scientists know about this process is substantial. We have detailed observations of multiple solar cycles, magnetic field maps of the solar surface going back decades, and increasingly sophisticated models of the interior dynamo mechanism. What we don't know is why some reversals are smooth and others are turbulent, why some cycles produce frequent strong flares during the reversal phase and others don't, and whether there are predictable patterns in the timing and characteristics of major active regions during the transition. AR 4366 might be answering some of those questions, or it might be raising new ones we haven't thought to ask yet. And then there's the wild card, the cosmic visitor, that has nothing to do with the Sun, but happened to arrive during this period of solar transition. In late December 2025, astronomers confirmed the trajectory and composition of 3I/Atlas, the third confirmed interstellar object to pass through our solar system. Unlike 1I/Oumuamua, which was rocky and cigar-shaped, or 2I/Borisov, which was a relatively typical comet, 3I/Atlas presents a more complex picture. It's definitely a comet, showing a coma and tail as it approaches the Sun, but the composition of that coma is unusual, dominated by carbon dioxide with detectable water and complex organic molecules. The solid science on 3I/Atlas is straightforward. It entered the solar system from interstellar space with a hyperbolic trajectory that confirms its extrasolar origin. Spectroscopic observations show emission lines consistent with sublimating volatiles, mostly carbon dioxide, and water ice. The nucleus is estimated to be between 1 and 2 kilometers in diameter, based on brightness measurements and assumed albedo. It will make its closest approach to the Sun in mid-February 2026, passing within approximately 1 astronomical unit of Earth's orbit, but not close enough to pose any collision risk. After perihelion, it will exit the solar system on a trajectory that will take it back into interstellar space, never to return. So far, normal cometary behavior. The speculation comes from the fact that 3I/Atlas is an interstellar visitor during a period of unusual solar activity, and some researchers have suggested, tentatively and with heavy caveats, that we should at least consider whether there's any connection. Harvard astronomer Avi Loeb, who previously proposed that Oumuamua might be artificial, has pointed out that the timing and composition of 3I/Atlas warrant closer examination. He's not claiming it's artificial, to be clear, but he is advocating for more observations and less dismissive skepticism when it comes to unusual objects from outside the solar system. The mainstream pushback is strong and well-founded. Every known comet we've studied in detail shows similar volatile-rich compositions. Carbon dioxide-dominated comas are unusual, but not unprecedented. The trajectory is entirely consistent with natural ejection from another star system during planetary formation or gravitational interactions. There's no evidence of artificial propulsion, no radio emissions, no anomalous thermal signatures. By all measurable parameters, 3I/Atlas is a comet, just one that happened to originate around a different star billions of years ago. The fact that it's passing through during solar cycle 25's maximum is interesting, but not necessarily meaningful. Still, the pattern is worth noting because patterns are how we find connections we didn't expect. Oumuamua arrived during the rising phase of this cycle. Borisov arrived during mid-cycle. Now Atlas is arriving during the magnetic reversal phase. 3 data points don't make a trend, but they do make you wonder whether there's something about the sun's magnetic activity that we're missing, some larger scale phenomenon that correlates with interstellar object arrivals. Or, more likely, it's pure coincidence, the kind of pattern humans are evolutionarily wired to see, even when no causal connection exists. Historical coincidences between solar activity and unusual astronomical events are easy to find if you go looking for them. The Carrington event of 1859 happened the same year as a bright comet visible to the naked eye. The Halloween storms of 2003 occurred during a period of increased meteor activity from the Leonid stream. You can always find correlations in complex systems because complex systems produce lots of data points. The challenge is distinguishing meaningful correlations from random coincidences, and that requires careful statistical analysis and, crucially, a plausible physical mechanism. Without a mechanism, correlation is just noise. So is AR 4366 an isolated flare risk, a sunspot that will erupt or not depending on local magnetic conditions, and then rotate off the Earth-facing disk to be forgotten? Or is it part of a connected cosmic narrative involving magnetic reversal, heliospheric changes, suppressed cosmic rays, and the arrival of an interstellar visitor? The honest answer is we don't know yet. The safe answer is that AR 4366 is a solar active region behaving according to known physical processes, even if the timeline is compressed and the context is unusual. The speculative answer is that we're seeing pieces of a larger puzzle that we don't have the full picture for yet. And speculation, when clearly labeled, is how science explores the edges of understanding. What we can say with confidence is that this isn't a normal moment in space weather, not because of mystical forces or alien influence, but because multiple measurable phenomena are converging in ways that challenge the standard models. AR 4366 is real. The cosmic ray suppression is real. The magnetic reversal is real. 3I/ATLAS is real. Whether they're connected in any meaningful way remains an unresolved mystery, one that might be answered by observations over the coming weeks, or might remain a historical footnote, an interesting coincidence during solar cycle 25. But here's what keeps me thinking. The universe doesn't care about our models. It does what it does based on physics we only partially understand. And sometimes, the evidence whispers things that don't fit neatly into the categories we've built. That whisper might be nothing. Or it might be the first hint of something we're about to learn. It's not just the sun, and it's not just one interstellar visitor. The cosmos itself is showing signs of variability that suggest our models of stellar behavior might need updating. Recent observations from telescopes studying other sun-like stars have revealed something both fascinating and unsettling. Rapid magnetic transitions, similar to what we're seeing in solar cycle 25, aren't unique to our star. They appear to be relatively common during stellar magnetic reversals, and in some cases, they happen even faster and more dramatically than what we're observing on the sun. This has implications for how we think about stellar aging, magnetic dynamo processes, and the predictability of space weather, not just around Earth, but around any planet orbiting any sun-like star in the galaxy. Observations from NASA's Transiting Exoplanet Survey satellite, combined with data from ground-based stellar activity monitors, have documented several cases of stars showing sudden increases in magnetic activity during what appears to be their magnetic reversal phases. These stars experience rapid emergence of large starspot groups, elevated X-ray and ultraviolet emissions, and in some cases, massive stellar flares orders of magnitude more powerful than anything the sun has produced in recorded history. The key finding is that these events aren't gradual. They're abrupt, appearing on timescales of days to weeks, much like AR 4366. This reframes solar cycle 25, not as an outlier, but as part of a broader astrophysical pattern. If rapid magnetic transitions are common during stellar magnetic reversals, and if our Sun is currently undergoing such a reversal, then what we're seeing might be entirely expected behavior that we just haven't recognized yet, because our detailed solar observation baseline only covers a handful of complete cycles. We've been watching the Sun with modern instruments for maybe 5 complete magnetic reversals, depending on how you count. That's a tiny sample size when you're trying to understand processes that might vary significantly from cycle to cycle. The telescopes revealing these stellar magnetic changes include both space-based and ground-based systems. The Kepler mission, during its extended K2 phase, captured light curves of thousands of Sun-like stars with sufficient precision to detect star spot modulation and flare events. Some of those stars showed activity levels that spiked dramatically during periods that stellar models suggest correspond to magnetic maximum and reversal. Ground-based systems, like the Solar Stellar Spectrograph at Lowell Observatory, have been monitoring chromospheric activity indicators in solar analogs for decades, building up a database that shows enormous variation in how different stars express their magnetic cycles. What these observations suggest is that the standard solar model might be conservative, built on observations from a relatively quiet period in the Sun's long-term history. There's growing evidence that the Sun's magnetic behavior during the 20th and early 21st centuries was unusually calm compared to its activity levels during earlier centuries, based on cosmogenic isotope records and historical auroral observations. If that's true, then what we're calling unusual about solar cycle 25 might just be a return to more typical behavior for a Sun-like star during magnetic maximum. The context for all of this includes 3I/Atlas, which remains under observation as it approaches perihelion. NASA's Psyche mission, while primarily designed to study the metallic asteroid Psyche in the main belt, has been tracking the trajectory of Atlas using its optical navigation cameras to refine orbital models and trajectory predictions. These observations have confirmed the comet's hyperbolic orbit and provided additional spectroscopic data on the composition of its coma. The science is straightforward. We're watching a chunk of ice and rock from another star system pass through ours, and we're taking every opportunity to gather data that might tell us something about conditions around that distant star when Atlas formed, billions of years ago. But here's where the cosmic context gets interesting. Atlas is the third confirmed interstellar visitor in less than a decade. Before 2017, we had 0 confirmed interstellar objects passing through the solar system. Now, we have 3. Either detection methods have improved dramatically, which they have, or the rate of interstellar objects passing through the inner solar system is higher than previous models predicted, or both. Recent studies suggest both are factors. Better telescopes and better sky surveys have increased detection efficiency by several orders of magnitude. But even accounting for that improvement, the detection rate suggests there might be thousands of interstellar objects passing through the solar system at any given time, most of them too small or too dark to detect with current instruments. The speculation, and it is speculation, is whether interstellar matter, even if not causally connected to solar activity, might be a signal of wider galactic conditions. The Milky Way's local interstellar medium, the region of space our solar system is moving through, has variable density and composition. We're currently in a region called the local interstellar cloud, a relatively low-density bubble surrounded by higher-density regions. As the solar system moves through galactic space at approximately 230 kilometers per second, we encounter different interstellar environments. Some researchers have proposed that changes in the local interstellar environment could affect the heliosphere's size and shape, potentially influencing the cosmic ray flux, and even, through mechanisms that remain highly speculative, solar magnetic activity. The evidence for such a connection is weak at best. The timescales don't match up well. The solar system takes thousands of years to move through major changes in interstellar environment, while solar cycles operate on timescales of 11 years. There's no known physical mechanism by which a slightly higher density of neutral hydrogen atoms in the local interstellar medium would trigger magnetic reconnection events on the Sun. The interstellar magnetic field is orders of magnitude weaker than the Sun's own magnetic field. So, any connection would have to be subtle, indirect, and probably undetectable with current measurement precision. But the broader point remains. Large-scale magnetic phenomena across multiple stars, combined with the passage of interstellar objects through our solar system, combined with unusual solar cycle behavior, all happening during the same general time frame, creates a narrative that's hard to ignore, even if the connections aren't causally proven. It's the kind of convergence that makes you wonder whether we're missing something big, some organizing principle, or mechanism that operates on scales larger than we typically consider when thinking about space weather. Or it's all coincidence, different phenomena operating independently based on different physical processes, and we're pattern matching because that's what human brains do. The recent findings about other stars showing rapid magnetic transitions similar to our Sun are solid science. The observations of 3I/Atlas are solid science. The cosmic ray suppression is solid science. What's not solid is the connection between them, if any connection exists at all. And that's where we are in early February 2026, sitting with multiple data streams that individually make sense, but collectively raise more questions than they answer. AR 4366 is rotating toward Earth-facing position. Atlas is approaching perihelion. The cosmic ray flux remains suppressed. The Sun's magnetic poles are in the process of reversing. Each of these is a known, documented phenomenon. Whether they're chapters in the same story or unrelated events that happen to coincide in time, that's the question that keeps solar physicists and astrophysicists up at night. And the final piece of this puzzle is perhaps the most frustrating. Our ability to predict what comes next is still limited by fundamental gaps in understanding and technology. Even our smartest tools can't yet see what's coming, and that reality is part of the story. Over the past decade, artificial intelligence and machine learning have revolutionized many fields of science, from protein folding prediction to gravitational wave detection. Space weather forecasting has been part of this revolution, with AI models trained on decades of solar observations, learning to recognize patterns that precede flares, coronal mass ejections, and geomagnetic storms. These models can process enormous amounts of data from multiple instruments simultaneously, identifying subtle correlations that human forecasters might miss. In some cases, they've shown impressive accuracy in predicting flares 24 to 48 hours in advance. But AR 4366 is teaching us the limits of these systems. The fundamental challenge is that AI excels at pattern recognition, but struggles with true novelty. Machine learning models are trained on historical data, learning statistical relationships between observables and outcomes. When a new situation closely matches something in the training data, the model performs well. When a new situation is genuinely unprecedented, the model has no basis for prediction and either fails or produces unreliable forecasts. AR 4366's 36-hour emergence doesn't have many close analogs in the observational record. Most active regions in the training data developed over longer timescales. So the AI models trained to predict flare probability based on active region evolution patterns are working outside their validated range. This distinction between pattern recognition and physical causation is crucial. A neural network can learn that certain magnetic configurations in sunspots correlate with a high probability of flaring, but it doesn't necessarily understand the physics of magnetic reconnection, the plasma dynamics of the solar atmosphere, or the subsurface processes that create magnetic flux emergence. It's matching patterns, not modeling mechanisms. For most forecasting tasks, that's sufficient. Patterns often reflect underlying physics, even if the model doesn't explicitly represent that physics. But when you encounter a situation that breaks the patterns, you need mechanistic understanding to extrapolate correctly. Recent breakthroughs in AI space weather forecasting have been notable. DeepMind's GraphCast model, adapted for solar physics applications, has shown skill in predicting geomagnetic indices based on solar wind measurements. The model treats the solar terrestrial system as a graph network, with nodes representing different spatial locations and edges representing physical connections. It can forecast the K-index and D sub-ST indices with reasonable accuracy several hours in advance, giving grid operators and satellite controllers additional warning time. That's valuable and potentially life-saving during severe geomagnetic storms. But there have also been notable failures. During the severe solar event of January 2026, several AI models predicted only moderate geomagnetic disturbance based on the observed CME speed and magnetic field measurements from upstream solar wind monitors. The actual geomagnetic impact was significantly stronger than predicted, reaching severe storm levels and causing unexpected disruptions to satellite operations and radio communications. Post-event analysis suggested the models failed to account for complex magnetic field interactions between multiple CMEs that were launched close together in time. The models treated each CME independently, missing the fact that they would interact and merge in transit, creating a more geo-effective combined structure. This gets at a deeper issue with forecasting complex nonlinear systems. The sun's behavior emerges from interactions across multiple scales, from the granular convection cells on the photosphere to the global magnetic field structure to the interior dynamo processes. Small changes at one scale can cascade to large effects at another scale through feedback loops and nonlinear amplification. Traditional physics-based models struggle with this complexity because solving the full set of magnetohydrodynamic equations for the sun's interior and atmosphere requires computational resources that don't yet exist. AI models struggle with it because the training data doesn't capture enough examples of these cross-scale interactions to learn reliable patterns. Next-generation observation systems are critical for improving both AI and physics-based forecasting. The Parker Solar Probe, currently making close passes of the sun's corona, is returning data from regions no spacecraft has ever visited. These observations of the near-sun environment are revealing details about magnetic field structure, plasma dynamics, and solar wind acceleration that weren't accessible before. The Solar Orbiter, a European Space Agency mission, is providing high-resolution images of the sun's polar regions and observing the sun from out-of-ecliptic vantage points that give a three-dimensional view of active regions and CME evolution. Ground-based systems are also improving. The Daniel K. Inouye Solar Telescope in Hawaii is producing the highest resolution images of the solar surface ever obtained, resolving structures as small as 30 kilometers across. That might not sound impressive until you realize the sun is 150 million kilometers away. These observations are revealing fine-scale magnetic structures, small-scale reconnection events, and details of sunspot evolution that were invisible to previous instruments. All of this new data will eventually feed into improved models, both physics-based and AI-driven, but there's a lag time between observation and understanding. Real-time monitoring systems like the Parker Solar Probe and Solar Orbiter are particularly valuable because they provide in-situ measurements of CMEs as they propagate through space. Instead of trying to predict CME arrival time based on remote observations of the eruption, we can directly measure the speed, density, and magnetic field of the plasma cloud as it passes the spacecraft. This reduces forecast uncertainty from days to hours for CMAs that pass near the spacecraft orbits. Of course, that only helps if the CME happens to pass near a spacecraft, and space is big, so coverage is still limited. 3. I/Atlas enters this discussion because a single interstellar visitor challenges our predictive assumptions in a different way. Before Oumuamua's discovery in 2017, models of interstellar object detection rates predicted we should find maybe one every few decades with existing survey capabilities. Finding 3 in less than 10 years means either the models were wrong about the population density of interstellar objects, or wrong about our detection efficiency, or both. This is a predictive failure of a different sort from solar flare forecasting, but it highlights the same underlying issue. Our models of complex systems are only as good as our understanding of the underlying processes and our sampling of the range of possible behaviors. For Atlas specifically, trajectory prediction is straightforward because it's a simple two-body problem once you have enough observations to constrain the orbit. Where uncertainty remains is in the non-gravitational forces, mainly outgassing pressure as the comet approaches the Sun and volatiles sublimate from the nucleus. These forces can slightly alter the trajectory, especially for small comets, and they're difficult to predict because they depend on the comet's rotation state, composition, and internal structure, none of which we can measure directly from Earth. So far, Atlas's trajectory matches gravitational predictions within measurement uncertainty, suggesting outgassing forces are relatively weak, but close monitoring continues. The synthesis of all this is that whether or not AR-4366 produces a major flare over the next few days, the real story is our improving, but still limited ability to predict what the Sun will do. We've made enormous progress. 50 years ago, we couldn't predict flares at all. 20 years ago, we could give probabilistic forecasts with modest skill. Today, we can forecast some events with high confidence and useful lead time, but we still can't predict rapid active region emergence. We still struggle with forecasting the magnetic configuration of CMEs. We still miss important cross-scale interactions and nonlinear amplification processes. Artificial intelligence will continue to improve these forecasts as more data becomes available and models become more sophisticated. But AI alone won't solve the problem, because the problem is fundamentally about understanding physics in complex, chaotic systems. You need both: mechanistic models that capture the essential physics, and data-driven models that can recognize patterns too subtle for human forecasters to spot. The future of space weather forecasting is probably a hybrid approach, combining physics-based simulation with AI pattern recognition, cross-validated and constantly updated as new observations become available. The danger isn't just the storms themselves, it's how unprepared we are for the unpredictable. Our technological infrastructure, satellites, power grids, navigation systems, assumes a certain level of space weather severity based on historical observations from a limited time period. If the Sun is capable of behavior significantly outside that historical range, and the evidence suggests it is, then our risk calculations are based on incomplete data. AR-4366 might be a warning shot, a demonstration that Solar Cycle 25 can produce rapid emergence events that catch us off guard. Or it might be an isolated case, interesting scientifically, but not indicative of broader trends. What we know for certain is that cosmic systems still hold surprises. The Sun is a complex, dynamic object that we're still learning to understand. The heliosphere is responding to solar activity in ways that don't perfectly match our models. Interstellar visitors pass through our solar system more frequently than we thought. Other stars show magnetic behavior that suggests our Sun might be capable of things we haven't seen yet. And our ability to predict, while improving, still falls short of what we need for truly robust space weather forecasting. So as AR-4366 rotates into Earth-facing position, as 3 I/Atlas approaches perihelion, as the Sun's magnetic poles continue their slow reversal, we watch and measure and model and forecast. We've built an impressive array of instruments to monitor our star. We've developed sophisticated models to interpret the data. We've trained AI systems to recognize patterns and predict outcomes. And yet, despite all of this, the Sun can still surprise us. It can still produce events that fall outside our predictive frameworks, that's not a failure of science. It's a reminder that the universe is larger and stranger than our models, and there's always more to learn. The story of AR4366 isn't finished yet. It might end quietly, the active region producing only minor flares before rotating off the visible disk. Or it might validate the forecaster's warnings, erupting with a powerful flare and geo-effective CME that tests our infrastructure and our preparedness. Either way, it's added another data point to our understanding of how the sun behaves during magnetic reversal. And those data points are how we improve our models, refine our forecasts, and slowly, gradually, learn to predict the unpredictable.